Hi, so this is the third alum video, the last one we will show. So as you can see here, there has been some crystal growth as you're comparing it to the last video. We're seeing more on the bottoms and some more on the sides. I'm still not getting that one like giant crystal that like would have been a great result, and as I discussed in the last video, that could be due to results with impurities in the alum or things messed up in the lab, like things spilling, which I discussed in the last video. As for any environmental changes, it stayed in the same place in my room on a shelf. It has been a little colder outside, so it's possible that that has affected it, but I don't think the temperature in my actual room has changed that much, so I don't think there has been any environmental differences. So as to explain the science of what's happening, pretty much the crystals form when a solution becomes supersaturated, and we in the lab we did saturate the solution, and a solution has achieved a maximum equilibrium concentration at saturation, and as more water and water evaporates, the solution goes from saturated to supersaturated, and as the water leaves, the ions are forced to react with each other, which causes the crystal to grow. And obviously, as the ions are reacting to form the solid crystal, that means the concentration of the solution is decreasing, which pushes it back to the equilibrium, value, and that is partly in reference to the University of Santa Barbara site on this, and I will cite that. But in terms of my crystal, I think one thing that could have been made better would have been to supersaturate the solution even more. We did a 40 milliliter solution since these were the directions. We could have added more and maybe put it on the hot plate or use the stir bar, the magnetic stir bar, to add more, to dissolve it even more. Alright, as for the scientific significance of despacing, pretty much despacing is important because by combining X-ray diffraction and the Bragg equation, it allows us to calculate the despacing, so the distance in the path lengths, and that gives us what's known as the fingerprint pattern into the sample crystal structure. That gives us insight into the structure of the lattice. And one medical application of this, I found a study that I'll cite called Medical Applications of Diffraction Enhanced Imaging, and they're using X-ray diffraction and Bragg's equation to include X-ray imaging to treat breast cancer. And as for the math of this, as you can see here, I used Bragg's law, which in its simplified form is 2d sine theta is n wavelength. We get the wavelength and the 2 theta value. The wavelength is over here in the graph given, and the 2 theta value, we're looking at the tallest peak, which I decided was around 20.5 degrees theta, which means that theta is 10.25 degrees. And with a wavelength of 0.15418 nanometers, you can solve for d by dividing that wavelength by 2 sine of 10.25 theta, and that gives you the distance of 0.4332. And so yeah, that gives us the distance in the path lengths, and using that and more like computer imaging, we could actually get an image of the lattice structure. Thank you.